Okay, in this video, we're going to go through examples 9 and 10. What I would do before we get started, though, is I would pause the video and try example number 9 by yourself. This is very, very similar to example number 8. So take a second to read through it, try and draw the picture, take the derivative of the function, and then come back here and check to see how you've done. All right, so we know that water is draining into a conical tank. So that is a cone-shaped tank with the vertex down. And water is draining into the tank at a rate of 2 meters cubed per second. So as the water is draining into the tank, we are filling that tank up. And so as we fill this up, we are going to be talking about its volume. And we know that the volume rate, so dV dt, is 2. We know the tank itself is 16 meters high, and the radius at the top is 4. How fast is the water level falling? Oh, I'm not filling this up. I'm draining water from it out the bottom. All right, so how fast is the water level falling, which is going to be dH dt. When the water level is 12 feet high. So this is similar to the pile of sand problem that we did yesterday. When we talk about the volume of our cone, we have too many variables in it. We have an R and an H. So if we take the derivative right now, we'd need to do product rule between R and H. And then we'd have a dr dt and a dH dt. We're looking for dH dt, but we don't know anything about how the radius is changing. So we're going to set a proportion up with the pieces that we know with the tank size that are constants. Because as the water is draining from here, the water levels are going down. And so the height and the radius are changing, but they're changing proportionally to the actual cone that we have. So I'm going to set up a proportion. My radius over my height is equal to my radius of the cone over the height of the cone. And now that I have this proportion, we could solve for whatever variable we want. I know I want to try and get rid of the R, and I want it in terms of H. So I'm going to multiply both sides by H in this equation so that my radius is equal to 4 over 16, or 1/4 H. And now I'm going to substitute in 1/4 H in for R. So my volume is 1/3 pi 1/4 H squared times H. Now before I take the derivative, I want to simplify this. So 1/3 pi 1/4 squared is going to be 1/16 H squared times H, which is going to be H cubed. And now we can go ahead and take the derivative. So dV dt, the 3 comes down in front of the H. So 3 times 1/3, those are going to cancel. Pi 1/16 H squared dH dt. And now we can fill in everything that we know. So we know dV dt is 2. Pi 1 over 16. H squared, H is 12. dH dt times dH dt. So I'm just going to simplify just a little bit more. 12 squared is 144 over 16 dH dt. So by multiplying by the reciprocal, I can solve for dH dt and get it by itself. So I'm going to have 2 times 16 over 144 pi. So to put this into my calculator, I'm going to go 2 times 16 divided by 144 pi. And we get an answer for dH dt. That is 0.071. And what are we talking about here with that? Is that this is meters per second, because we would label my height as meters. And so we have meters per second. Okay, let's move on to example number 10. In this one, suppose we have a 6-foot tall person, and the person is 10 feet away from a 10-foot tall lamppost. Now we know that the person is moving away at a rate, right here, of 3 feet per second is how fast they're moving away from that light post. So this one's already kind of labeled as X. I'm going to label this one as Y just so we have some different variables on it. And dy dt is going to end up being 3. And then I'm going to circle 10 because I'm going to circle all my constants because we know we can fill that in before we take the derivative. Now, when I look at this picture, how are we going to come up with a formula for this to figure out at what rate is the length of the shadow, which in this case is going to be x. So dx dt is the shadow changing. Now what we have here is we have a triangle that's created from the person to the end of the shadow back up in like the path of the light using that kind of angle there. And then we have another similar triangle that's the height of the light down on the ground all the way up and back up to the tip top of the light. And so since these are similar triangles, the equation that we are going to use is we're going to set up a proportion based on the triangles to help us figure out what dx dt is going to end up being. So here's what our proportion is going to look like. So the height of the light is going to be 10 over the height of my person, 6, equals, now look at this big triangle that's here. The bottom part on the ground all the way out to the top of the triangle is going to be y plus x. And I'm not putting in 10 feet because as this person's walking away, this 10 feet is changing. That's going to be the y that we're going to use later, but that one's changing for now. So y plus x. And then as I look at this other triangle, the smaller triangle, 6 is the height and x is the bottom of that triangle. So x is going to be on the bottom. Now, I don't really want to take the derivative right now because I'm going to have to do quotient rule here. So I want to get rid of the fractions. So I'm going to multiply by x on both sides. And I'm going to multiply by 6 on both sides. When I multiply by 6 over here on the left, these 6's will cancel. And when I multiply by x, both the x's will cancel. So on the left, I have 10 times x equals on the right 6 times x plus y, or y plus x. So 6y plus 6x, distributing that 6 out to both of them. Now I'm still going to even combine my like terms even more. I'm going to subtract my 6x from both sides. So I have 4x equals 6y. And now I can go ahead and take my derivative. So 4 dx dt equals 6 dy dt. And fill in what we're looking for. We're looking for dx dt, knowing that y is 10 and dy dt is 3. So we'll have 6 times 3, which is going to be 18, divided by 4. So 9 halves, or 4.5. And we can say that that is in feet per second. That's how that shadow is changing. Now, the last part is from this exact same picture that we have. So from those two triangles, one being the light post being 10 feet tall, and then that person being 6 feet tall walking away, what's the rate of the tip of the shadow changing? So how far is it moving away from the light post? So this distance right here, which I'm going to call Z, and I'm looking for then dz dt. So we can still fill in x. We know x is here, and we know y is over here. We also know that dy dt, which we found in the earlier one, is 3. And dx dt, which we found in the A portion, is going to be 4.5. So again, we're going to set up the proportion for the similar triangle, but now we're going to include z. So I'm going to go 10 over 6, the height of the lamppost and the height of my person. For the bigger triangle, I'm going all the way across from the light post out to the end of the shadow. And that was the length that we called z over, and then we have the smaller triangle right here, which we're going to call x. And then we're going to do the same thing. I don't want to do the derivative right now. I'm trying to find dz dt. I don't want to do the derivative right now because I would have to do quotient rule. So I'm going to multiply both sides by x, and I'm going to multiply both sides by 6. On the left, the 6's will cancel, leaving me with just 10x. And over here, the x's will cancel, leaving me with 6z. And now we can go ahead and take the derivative. 10 dx dt equals 6 dz dt. 10, I know dx dt is 4.5 equals 6 dz dt. So 10 times 4.5 is going to be 45 divided by 6 to give me an answer for dz dt, which will be 7.5 feet per second. And so that's how far or how fast that end of the shadow, the tip of the shadow at the very end, how fast it's moving away from the light post, versus this one, which was how fast that shadow distance is lengthening.